Hello and welcome to lecture number 4. So where today we will be discussing about the kinetic properties of the colloids. So in last lecture we discussed about the forces that are responsible for stable colloids, and related to that the second most important property is the kinetic properties. So in this lecture, we are going to talk about the Brownian motion first, and then a little bit about diffusion and osmosis. So, we start with a very brief and elementary discussion on Brownian motion. We have already talked in the last lecture that below a critical size limit, some particles, or it could be molecules also, like it could be some macromolecules as well. It could be proteins, it could be certain polymers. So they exhibit a random zigzag motion in a suspension medium. So this is a very elementary picture that you have seen in your high school physics or chemistry textbook, that if there is a particle and then it automatically can undergo this random zigzag motion. Okay, so the zigzag motion which is completely random. So obviously the question is, what causes this motion? And there is a fundamental consideration between this zigzag random motion. So let's first talk about this. So a particle, when being suspended in a medium, and obviously the particle should be a small particle, and we have seen in previous lecture why the size range is so critical. And so below that size range, the particles undergo collision with the solvent molecules. So after collision, they change their course of their motion, and again they undergo subsequent collisions, and so they continue moving into that zigzag motion. And the kinetic energy they acquire, means the particle, is basically from their ambient thermal energy. So the most fundamental consideration regarding the Brownian motion, so we can write this is a fundamental consequence, the fundamental consequence of kinetic theory is definitely, it is the Brownian motion. But the most characteristic feature is the average kinetic energy. So we can call it the average kinetic energy of the particles or the macromolecules that are undergoing Brownian motion should be in the order of half kBt. So this K subscript B is the Boltzmann constant and T is the temperature at absolute to scale. So this average kinetic energy, this term kT, obviously perhaps you are familiar with that, it denotes the ambient thermal energy. So this average kinetic energy should be in the order of the kT, that is the, sometimes it is also called the randomization energy. So therefore, if we go by that, so then this average kinetic energy, average velocity of the particles undergoing this zigzag motion should be equal to root over of twice of kBt and divided by m. All right. So I'm sorry, the two term will not be there because the half cancels out. So now immediately you can see that for average velocity we have the mass term appear at the denominator. So that means larger the molecule means larger the molar mass or larger the particle, the average velocity going to be less, or in other words, so we come back to the same point, the smaller the particle or lighter the molecule, same thing, would have a larger average velocity for zigzag motion. Remember, this is the average of all the instantaneous velocity to have. The velocity is not constant throughout. This is just the average velocity. So, and then a more fundamental equation was proposed or derived by Albert Einstein. So remember, Albert Einstein did all this research on the Brownian motion much before he started working on photoelectric effect. Okay, so this is Einstein's one of the earlier work. So he derived a fundamental equation that related the Brownian displacement with the diffusion coefficient of a particle in a suspension medium. So I'm going to clean that board, and I would just like to mention that equation and one consequence of that Einstein's equation, which would be a little bit interesting to us, especially in the context of colloidal properties. So let's do that here. So here now we introduce the Einstein's fundamental equation related to Brownian motion. So here you see x bar is equal to root over of twice of d times t. So let me explain. So this x bar represents the Brownian displacement of the particle from original position. So this has the dimension of length, and the d stands for diffusion coefficient, and it's also known as mass diffusivity, and of course t is the time. So now before we proceed, you might be wondering that how is it possible to analyze or study the Brownian motion experimentally? So the answer is yes, it is quite possible. So people have observed Brownian motion of a pollen grain in water, and also using some colloidal suspension or a colloidal salt in water or some other medium, it is possible to follow Brownian motion. But the only constraint is the particle under question has to be visible all the time. So how do we visualize a particle in a suspension? The answer is through Tyndall effect. So Zsigmondy discovered or developed ultramicroscope. Through ultramicroscope, it was possible to follow the Brownian motion. And some other time we will discuss the basic working principle of an ultramicroscope under the optical properties of colloids. So all right, so that's coming back. X bar is equal to twice of dt, and now here we would try to relate this x bar, that is Brownian displacement, with the dimension of the particle. So to do that, we need to take the help of another equation, which is also known as the Einstein's equation for diffusion, and that equation is known as D, means the diffusion coefficient multiplied by F. So here F stands for the frictional coefficient, and it is also called as the coefficient of friction, same thing. So this is equal to, again, the Boltzmann constant multiplied by the temperature T. So from here one can try to relate the x bar with the dimension of the particle. So how? So that we can do it here. So therefore, the diffusion coefficient D, okay, is equal to, from here we can express this as kBT divided by F. All right, so F is the frictional coefficient. So now, what would be the value of the F? So remember, like we talked about the viscous drag force in the last lecture. So viscous F drag. So this drag force was described to be something like that, 6 pi eta. Eta is the dynamic viscosity multiplied by r. It is the radius of the particle provided the particle is spherical, okay, multiplied by some velocity of the particle through the medium. So, and in last lecture, in that context, we refer to this as the settlement velocity. So, so this is true for spherical particle. Okay, so for a spherical particle, this is the viscous drag force. Now, the same thing, okay, this F drag is denoted as F multiplied by V velocity. So this term 6 pi eta r stands for the frictional coefficient F for spherical particle. So that we have to remember. So this formula is true when we assume that the particle is spherical. So therefore we replace kBt divided by, in terms of in place of F, we write 6 pi eta r. Okay, so now we are going to clean the board and we express the equation further. So let's do that. So as we started to relate the x, means the Brownian displacement, with the dimension of the particle, so we need to further develop this equation a little bit. So already you see we got a relationship with d and this radius. Okay. So now what we can further do is we want to relate this with x bar. So we multiplied it with twice of t in the left side. So of course in the right hand side we multiplied with twice of t. Okay. And then this becomes x bar whole square according to this relation. Okay. So therefore this cancels out and we have 3. So therefore it becomes kb t multiplied by time t divided by 3 pi eta and r. So here r is the radius of the particle, provided we are talking about a spherical particle. So therefore what happens is obviously then x bar would become root over of kb t multiplied by time t divided by 3 pi eta and r. Okay. So now this equation can take a very interesting expression. So if we multiply the Avogadro's number with both the numerator and denominator, we get the following expression. So Boltzmann constant multiplied by the Avogadro's number is the gas constant, the universal gas constant. So this becomes R multiplied by T, temperature multiplied by time T, okay, divided by, we get 3 pi eta R and divided by R, means R multiplied by Na, the Avogadro's number. Okay. So from this, few interesting things happen. Okay. Firstly, so this is equal to x bar. So now Brownian displacement can be easily verified if we know, if we put the value of R, Avogadro's number, eta, and everything else. Okay. So now the most interesting thing that happened, that from studying this Brownian motion or by studying this X bar and T data, the scientist, the Swedish scientist, his name was Wedberg, in 1911 he used some gold saw, okay, means the colloidal gold particle, and he extensively followed the Brownian motion, and then he from that, so you think about that, if you know X bar, time t, radius r, eta and everything else, then indirectly you can verify or you can calculate the value of the Avogadro's number. And historically, that was the way to verify the Avogadro's number through an experiment. So from Wedberg's experiment, the Avogadro's number was calculated to be 6.0. At that time it was 6.09 multiplied by 10 to the power 23. So you see it is very close to the most accurate value known, that's 6.023 into 10 to the power 23. So that was a very successful experiment validating the Einstein's fundamental equation for Brownian motion. So anyway, if we keep the Avogadro's number as the 6.023 multiplied by 10 to the power 23, then following that, we can find out the values of R, means the values of X bar when we have a given values of R. So it has been found out that if R is equal to 1 nanometer, so we have a 1 nanometer sized spherical particle or a macromolecule assumed to be spherical, then this X bar, okay, becomes something around 1.23 millimeter. Okay, so you see that it is millimeter because it is inversely proportional. The smaller the value, the larger is this, and it becomes to 1 micrometer. Then this X bar becomes something around 39 micrometer. So this is nothing, this is almost negligible. So for a very small particle, you see we have a large Brownian displacement, 1.23 millimeters in macroscopic scale. So that's how, that's why I told you that in the previous lecture that when a particle is sufficiently small, it is capable of undergoing Brownian motion, so with a very large X bar, and that particle would never settle. Okay, it will always form a stable colloidal suspension. Now once the particle is larger, so the Brownian motion becomes negligible. Means Brownian displacement 39 micron is negligible. So then the particle is subjected to the two kinds of forces, the gravitational forces and also the viscous drag forces. And the balancing of the two would determine how big the V settlement is. Okay, so now the next topic we will talk about, so what we do if we find a colloidal suspension with a very small V settlement, that means it's a stable colloidal suspension. So is there any way we can separate the particles out from the suspension? So we will talk about that next, but before that I must tell you that this Brownian motion causes a very local disturbances of the concentration. Okay, and so therefore the second law of thermodynamics is not applied microscopically. So second law of thermodynamics is a macroscopic phenomenon. So why I'm talking about the second law of thermodynamics, because if we talk about the diffusion, so where the solid particles move from the more concentrated zone to a less concentrated zone, so you have a, means it will go to the more disorderedness to less disorder, from less disorderedness to more disorderedness. So it would follow the path of the second law of thermodynamics, but that is not applied on Brownian motion typically because it is a microscopic property, and second law is only applied macroscopically. Next we discuss how to settle the particles with a relatively small V settlement. So that we do next. So in this part we talk about the settlement velocity, so for which we have already found an expression in last lecture, and we have seen that for a particular suspension medium the V settlement is proportional with R square. So therefore in water, if we talk about a certain material, then for 1 micron size spherical particle, if the V settlement is 8 millimeter per hour, then if we reduce that radius to 1 nanometer, then the V settlement becomes 8 nanometer per hour. So 8 nanometer per hour means that if the particles are sufficiently small, it will take an almost infinite amount of time for them to settle down, or in other words, smaller particles would never settle due to the balancing out of the gravitational pull by the viscous drag force. Okay, so now the question is, if we need to settle the suspended particles, that means we want to separate the suspended medium from the suspension phase, how can we do that? Okay, so here we are going to talk about a technique. It's called ultracentrifuge. So the technique is called ultracentrifugation, and the equipment that helps to do that, it's called an ultracentrifuge, and it is basically developed by the scientists Redberg, and it is around 1926 or so. All right. So Redberg was a student of Zygmundi, who is another pioneer in colloidal science. So we utilized chemical effect to develop ultramicroscope. So as I told you that we are going to discuss it later. So what's the technique basically is, if you remember, there is a particle, and if the particle is is forced to rotate around the center here, okay, so the distance x from the center of rotation, and this is the particle, and the particle's mass is m, and the particle undergoes a circular motion like that, then and the particle rotates with an angular velocity omega, then the F centrifugal force that would act on the particle should be equal to m omega square multiplied by x, the distance from the center of the rotation. Okay, so therefore what happens to the colloidal suspension? So if we take the colloidal particles in a centrifuge tube, something like that, and this is the suspension medium, and the particle is over here, and in normal condition the V settlement is very small, the particle won't settle. So now we are going to put a centrifugal force on the particle just by rotating that tube under very high velocity. So before we proceed, we have to consider that we can assume that the suspension medium is water. So therefore, we have to talk about the apparent mass of the particle when it is submerged in that suspension medium. So the apparent mass, that means it is actually the buoyant mass. So the apparent mass of the particle, means the colloidal particle, or the particle is in question, should be equal to the mass of the particle itself minus the mass of the volume, or mass of the liquid is displaced. So the mass of the water it displaces would be the volume that it displaces multiplied by the density of water, isn't it? And then what we can do more is we can slightly twist this equation like this, means we just change the expression that we multiply m over here and also divide the displaced liquid by m, and then we have rho w. So this quantity V displaced divided by m becomes the displaced volume per unit mass of the particle. So that would become once again m minus m multiplied by V bar rho W. So this V bar displaced is called the specific volume of the displaced liquid, or in other words, the specific volume of the particle itself. Okay, so therefore it can also be written as m multiplied by 1 minus v bar, or specific volume of the particle, multiplied by the rho W, that is the density of water. So therefore we have an expression for the apparent mass of the particle is this. Okay, so now we are going to equate that if the centrifugal force is applied on the particle of this mass, then what would be its settlement velocity. So let's clean the board and just work it over here. So therefore, we consider this scenario. So we have taken our particle in question in a centrifuge tube, and we are applying a centrifugal force on the particle. So in that case, the centrifugal force can only be opposed by the viscous drag force, okay, offered by the suspension medium. So now we have seen that viscous drag force can be written as the coefficient of friction multiplied by the V settlement is equal to, now this is the apparent mass we have calculated, multiplied by omega square x. So now, following Einstein's law of diffusion, we can replace frictional coefficient F by kBt multiplied by the T, that is the diffusion coefficient, and velocity we change it to dx dt since the x is here, and the rest of the equation looks like this. So therefore, from this we can try to find out the value of d, that is the diffusion coefficient. So the value of d then becomes something like this: kBt multiplied by dx dt whole divided by m multiplied by 1 minus v rho w omega square x. All right, and then what happens that we can again change this expression a little bit by multiplying Avogadro's number both numerator and denominator. So this becomes Na kb t dx dt, and of course Na kb is actually the universal gas constant R. So now when we multiply m multiplied by Na 1 minus V rho W omega square x. So now please remember that the mass, if we talk about a molecule, then this mass would be the mass of a single molecule. So if we multiply that with the Avogadro's number Na, so then we get the molar mass, isn't it? So, or in other words, the molecular weight. So m becomes the molar mass. All right. So then, therefore, the same thing can again be expressed something like RT multiplied by S, a constant, divided by m multiplied by 1 minus V rho W. Okay. So here S stands for a constant. So here x becomes dx dt divided by omega square x. So this S is called the sedimentation coefficient. So this is a constant, and you see that it depends on the settlement velocity, also on omega square, or basically omega, the angular velocity. So the smaller the angular velocity, the larger S, and vice versa. Okay, and x obviously is the distance of the particle from the center of the rotation. So why we are considering all this? Because that now if we look at this equation at the bottom that we have just got, so I'm going to erase that part and we'll simply write this thing: d is equal to RTS divided by m 1 minus v. So this equation that we have got, So if we have a particle or basically a molecule, a macromolecule like protein, something like that, and if we know the molar mass, and from the centrifuge machine, from the parameters we can find out S, and we know all these things, we can easily find out the D. Okay, but the major utility of this method is not to find out D like this, but it lies somewhere else. The thing is, now if we just exchange this thing with that, so that M becomes RTS divided by D multiplied by 1 minus V bar rho W. So now you see the tremendous utility of this equation. M is the molar mass. So now you take something like a macromolecule like protein, whose molecular weight you don't know, molar mass you don't know. Then you do the centrifugation, find out S, and obviously R, T, V bar and rho W all known. And then you calculate D. So the diffusion coefficient D can be calculated by various methods. So one of the methods is known as the porous plug method. Okay, and there are other methods also. So if you apply these methods like this porous plug method, or another method is called the sedimentation method. Okay. So these are some standard practical methods. So if you use this method and find out D, you can find the molar mass M. So that is the huge utility. So for unknown proteins, you can find out the molar mass obviously in kilodaltons. So, and this technique was again developed by Wedberg, and not only that, using this technique, Wedberg, he was able to separate hemoglobin from a different mixture of proteins. All right, and further, following Wedberg's technique, it is possible to isolate different cell organelles, components of an animal cell using this ultracentrifugation technique, because different cell components would settle down under different centrifugation omega. So that means under different RPM, different angular velocity, the different components of cell will be settled down, and it is relatively easy to separate those. So therefore this ultracentrifugation technique had a huge utility, and due to which Wedberg was awarded Nobel Prize. Okay. And so just let me tell you, so he coined the term ultracentrifuge. So he loved the term ultra. When Zygmundi developed a microscope, we call it ultra microscope. So this term ultra means looking beyond. Okay, so that means something that is not observed generally, so you are looking it beyond. So that's why it is called ultracentrifuge. So using this technique, one can go up to like 400,000 G. Okay, so let me write it over here. So you can increase the acceleration due to gravity up to 400,000, sometimes even 1 million G, and you can achieve a rotation per minute as high as 100,000. Okay, so 100,000 RPM can be possible in an ultra-centrifuge machine. So these days, in the common laboratories, these ultra-centrifuge machines are available. So sometimes you can go check in one of the ultra-centrifuge machine, and you can try to settle some nice colloidal suspension, which is not otherwise cannot be settled down. You do some ultracentrifuge and you try whether you can settle the particles at the bottom. Okay, so this comes under the kinetic properties of the colloids. That's why we talked about the basic technique of this. So next we are going to talk about two things which are already known to us, that is diffusion and osmosis, as quickly and as basic manner as possible. So let's do that. So let's quickly recapitulate some basic principles of translational diffusion. So as a definition, remember, it's the transport of mass in nature without requiring the bulk movement. So whenever the medium, that means also in terms of the colloidal science, the suspension medium is referred as the bulk medium. So for example, if we talk about some solid particles, that means solid particles suspended in a liquid. So if the bulk liquid moved by some convection motion due to some heating or some other disturbances, we don't consider that as a diffusion. So that means the bulk medium has to be stationary, and the solute, so that means the suspended particles should undergo mass transportation. So there would be a net flux when the particles are actually moving from a concentrated region to a less concentrated region, and when an equilibrium is established like that, so then there is no net flux. So this diffusion movement is governed by Fick's first law. It is one of the fundamental laws of the kinetic properties. You can treat them as Newton's laws. So the first law says that dm means basically the amount of mass that is getting transported, means is a very small amount, is equal to minus d stands for the diffusion coefficient multiplied by the a. So basically a is the area through which these mass of m, these particles are passing through, and dc dx is the concentration gradient. So quite often we come across a term called the diffusion flux. Okay, so let's make ourselves familiar with the term diffusion flux. So this thing same can be represented as dm divided by a is equal to minus d dc dx. So this term dm over a is also called the diffusion flux. So that means the number of particles passing perpendicularly through area A, or passing per unit area. Okay, once you divide the dm divided by a, so that means it is the number of particles, or the actually the mass passing through per unit area is the diffusion flux is equal to minus diffusion coefficient multiplied by the concentration gradient. So this is the first law, and so once the diffusion coefficient is known, we can calculate the diffusion flux, provided we can calculate dc dx. And then so you see this equation is independent of time. So the time derivative comes in the Fick's second law, where the dc dt, that means the change of concentration with respect to time, can be correlated with the second derivative of c with respect to x. So that means d2c dx2. So it is the relationship between dc dt with d2x dx2 comes from, so that relationship is established in Fick's second law of diffusion. So these are few fundamental considerations for diffusion, and so if we come across anything or any terms related to this in this colloidal science course, so it would help us to make familiar with the terms. So next we quickly discuss about some basics of osmosis in the same manner. So lastly we talk about the osmosis. So it's defined as the net movement of solvent molecules, mind that, through a partially permeable membrane from lower solute to the higher solute concentration. So this is explained something like that. So we have two tubes, U tubes, and so we have a partially permeable membrane separated by the two mediums with two different densities. Two different concentrations. So here we have high concentration, we have low concentration. So if it is separated by partially permeable membrane, that means which does not allow the suspended solutes or the particles through the membrane. It only allows the solvent molecules to pass through, or that means the bulk dispersion medium to pass through. So the dispersion medium from the lower solute concentration side, it will diffuse to the other direction, that means to the higher solute concentration. And this movement of solvent molecule will continue till we have an equilibrium where the concentration of both sides are equal. And if you look at the situation for this U-shaped tube, that obviously the volume of other side has been increased, and the other side has been decreased. So this is the difference of height, delta H, with respect to the initial position. Now, at equilibrium position, you need a pressure to keep this equilibrium situation. So that pressure is called the osmotic pressure. So it says the pressure required to maintain the equilibrium with no net movement of solvent. So as long as the pressure is there, there will not be any movement of the solvent. So that pressure is called the osmotic pressure, and it is denoted as pi. And this movement of solvent from the lower solute to the higher solute concentration can be explained in terms of entropy or free energy, following the concepts of statistical thermodynamics. And remember, this pi, the osmotic pressure, is a colligative property of the solvent, of the medium. So this pi can be expressed something like CRT multiplied by 1 over m plus B2C plus B3C square, and plus some other terms. So what I want to tell you that this here, these M stands for the molar mass, okay, and this B2, B3 are different constants, and the T is obviously the temperature in Kelvin scale, R is the gas constant. So the colligative property means that basically it does not depend on the nature of the solute, but it would only depend on the concentration of the solute. So probably you heard about the swelling of gel. So this is the osmosis can be applied in the context of gel swelling. So swelling of gel is a very interesting and useful phenomenon in colloids and surface science, and I have already explained that gel is a type of important colloid. So the gels can be swelled when the dispersion medium goes into it. So the boundary of the gel may itself act as a semi-permeable or partially permeable membrane, and so the osmosis process can take place there in the phenomenon of gel swelling, and this gives rise to a very important biophysical and biomedical application, which we may learn later some more about it. So today's lecture then sums up a few very fundamental aspects of kinetic properties: Brownian motion, sediment velocities, ultracentrifugation, diffusion, osmosis, etc. So we have to keep those basic principles in mind when we move forward and apply some of these principles to understand more about the fundamental properties and applications of colloids and surfaces. So we finish our lecture here today. So in next lecture, number 5, we will talk about the electrical or electrokinetic properties of colloids, which is one of the most important properties we are going to learn in this course. So you please keep watching the video lectures, and I see you in the next lecture, and stay safe. Till then, goodbye.